So, hello everyone. I'm Jeffrey. I am a cyber officer. I'm here to present packet capture today, along with.
Hello, guys. My name is Peter. I'll also be presenting the packet capture workshop today.
Hello, I'm Henry. I'm a second year CS major, and I'm the third presenter.
All right. So I guess we're all ready to go. All right. So let's start off this workshop with a basic question: how do computers communicate? Well, how do people communicate? Well, someone has to first initiate a conversation. You can't just say, "What's the weather like?" before you say hello, right? So first, someone initiates the conversation, and then you guys talk in a certain language, like English, and then that's how you interchange information. Well, similarly, computers communicate over the network via a set of common languages known as protocols. So in my analogy, that would be the common language, like English, would be protocols, and basically they define how to have a conversation. But protocols are a little special in the way that they work because they actually work together to basically define the rules of the conversation. So we can explain this a little bit better by grouping these protocols into the TCP/IP model, where there's different layers, and each of these layers have different functions, and each of these layers communicate with each other. There's also the OSI model, which is a more in-depth kind of version of this, but for now, we'll only consider this model. So you have your network interface at the bottom. So that's basically the where the wire is. And then you have the internet layer, which is where the IP addresses gets resolved. And then you have the transport layer, which kind of defines um, how to ensure packets get to their destination. And then finally, you have the application layer.
All right. So to, I guess, talk about these layers, you can kind of think of them as an onion. So as you see, can you go back to the previous slide, please? Yeah. So the application layer would be your innermost layer, and then outside of that is the transport layer, and then outside of that is the network layer, and then the physical layer. To talk a little bit more about these individual layers, the application layer is the abstraction layer that provides the interfaces and protocols needed for users. So for example, web pages, login services, the format of emails, that's determined and handled within the application layer. The transport layer is responsible for delivering data between communicating hosts. It's responsible for the order of packets and flow control, which means making sure that the transmitter does not send more data than the receiver's buffer can hold. And then we have the network layer, which is responsible for path finding between two networks. The internet is a vast, interconnected web of various networks. So when you hear about routing algorithms and routing tables, this usually refers to the network layer. And then lastly, we have the physical layer, and that corresponds to the bit level transmission and the physical medium in which the data is carried through. So when you hear about twisted cable pairs or fiber optic, that usually refers to the physical layer. All right, so we have TCP and IP, which is pretty much going to be the backbone of a lot of what we're talking about today. So TCP creates a stream of data by dividing it into chunks and creating a TCP segment. And this segment, you'll see information such as the destination port, source port, sequence number, and ACK number. And then this information is basically provided for flow control, right? It's to ensure packet reliability and ensures that no data is lost. And then we also have IP protocol, which ensures that packets are sent to the correct IP address. So TCP and IP kind of work in tandem to create, the TCP IP protocol suite to ensure that data is sent to the correct host and that data is reliable. Okay, and so then we have IP layout. So the left is an example of an IP header, which you'll find on an IP packet. Some important things to know is the source address and the destination address. And on the right-hand side is an example of an IPv4 address. So each octet, which is like the 8 bits, range from 0 to 255. And although some addresses such as like 0.0.0.0 and 255, 255, 255, 255 are reserved. So you can't use those addresses. But each computer on the network will have their own individual IPv4 address, and you'll see that in some of the challenges later. Next slide. Okay, so DNS. What is DNS? So DNS stands for Domain Name System, and it's responsible for translating domain names into IP addresses. What is a domain name? So like if you're typing, let's say like www.google.com to your browser, that's google.com is the domain name. And so what will happen is that when you search for google.com, first your computer is going to check your local DNS cache, which is essentially looking for the corresponding IP address for the host name. If it can't find it, then a DNS query is issued using UDP port 53 to a local DNS server. And then the DNS server is going to actually query other DNS servers to resolve some parts in the host names. That's why we consider domain names as hierarchical, having a tree structure. It's because like there's some stuff done behind the scenes within the DNS server to give your browser back the translation. If you're wondering about how this process works, on Windows you can use the command ipconfig/display-DNS, and that will give you the table, your local DNS table with the translations for IP address and host names. And if you're on Linux, you can use dig and then website like wikipedia.org to find the local DNS corresponding DNS translation.
That's right. All right. Going along the same vein of what happens when you search google.com, we'll talk about HTTP, which is a hypertext transfer protocol. So basically, this is what you use to surf the web. It's specifically the application layer protocol for transferring hypermedia documents. And so it follows the basic client-server model in which you obviously request something and the server gives you a response. So going more depth into the request response format. Next slide, please. You can see here that this is an HTTP request. So yeah, so basically it starts off with a request line, which basically defines the method of what you want to send. So there's get requests, which is get is usually for getting information, and post is usually for like modifying information. So like if you're changing your username in the database. And then there's headers. So each of these headers are kind of like first of all, they follow the form of field : value, and then they also describe like what the client wants when it gets its response. So like here it says it accepts gzip, deflate, and it wants English. And finally, there's the body, and that's where like the query data is, for example. So like when you search on Reddit for hello, then it would show up like in here on the URL as like search !q equals hello. And so that would be the query data. Next is the HTTP response. And so this is what you get when you actually search for something and then in your browser. And then you can actually see the response data if you inspect the web page and then you go to your network tab. So first, there's the status line, which says the HTTP version and also the status number. So 200 would mean OK. And then next, there's the headers. Once again, this time it's describing the document return. And finally, there's the body, which describes, which is the returned web page, and that's just it's just a JSON of the HTML and everything else. So going on about other types of protocols that might be useful, and that you will definitely be using in your daily life sometime if you've been on the internet. Anyway, there's UDP, which is basically TCP, but it doesn't guarantee that the packets will transfer. There's VoIP, which is voice over internet protocols, which is used in telecommunication. There's P2P, which is peer-to-peer communication, so for like peer-to-peer networks. Then there's LAN, which is a local area network protocol, so over Ethernet cables. And then there's RTP, which is basically real-time transfer protocol, and that's for streaming media. And so if you want to look more information, there's the Wireshark wiki right there.
Let's go back to the previous slide real quick too, because I think there was a question
value?
about the value.
Oh, like the field value thing. So like the field would be the date, and then the value would be the actual date. So like Sunday, February 8th.
Okay.
Did that answer your question?
Isaac, does that answer your question?
Yeah. Yeah, it's just format.
And then what part is the body? That would just be the HTML. So everything below this orange line is considered the body.
Oh, so like there are situations in which you don't want to guarantee that you get packets. For example, Zoom. If Zoom used TCP, that would be incredibly slow. And you're like, if you had a really bad connection, you would basically have every single frame of you would still get every single frame, but it'd be like really disjointed. But in that situation, you'd rather just get like a cut to the next when your connection comes back. Like, and there's also like a significant overhead with TCP. Yeah.
Okay. Always used for local network.
Well, that specific one, I believe, is what's it called again?
The 192.168 block is set aside by the, I think it's ICANN that designated that, but it's set aside specifically for internal networks. So you know that a 192.168 will never show up as like a public IP address. Similarly for the 10.x.x.x block, those are both solely for internal networks.
Yeah, so just to follow up what Matt said, I think, yeah, there's a separation of IP addresses, specifically IPv4 into classes. So 192.168 would fall under a class C network, and I think there are like various other standards, like I think 127.0.0.1
is always localhost.
Always localhost. So.
Yep. Feel free to ask any other question right now because we're about to jump into the demo.
Yeah, let's just make sure that you guys understand it right now.
Yeah, I'm gonna give like another 30 seconds before I move on to demo. But if no one has any questions, I'll go ahead and move on. Okay. So for this next part of the presentation, we're going to sort of do a live demo of Wireshark and also some information that Jeffrey and Peter has covered throughout the slides, just so you guys have a better understanding. And also, you're probably going to want to use Wireshark when you do our challenges later after the presentation. So inside the prerequisite, you should have installed Wireshark already. You don't need it right now since I will be running Wireshark on my end for you to see. So let me open up Wireshark. So the first, oh, by the way, if you guys have any questions throughout, feel free to stop me or put something in the chat. I have chat pulled up on the side in case you need me to slow down and explain something again. So on the right-hand side of my screen, you see that I have the Wireshark browser open. And this is probably something that you'll see, you cannot see Wireshark. So again, this is what Wireshark will typically looks like when you open it up. And below you'll have like the various different network you'll be able to connect to and analyze. In the event that if you don't have any of these network listed, there's a very good chance that you didn't install it correctly or the WinCap. And if that's the case, hop into the main room and one of us will help figure out why that is for you. But generally for our challenges, the packets have been pre-captured such that you don't need to analyze it directly on your network. Okay, so continuing on, if you can see down here, I have some Bluetooth net connection. I have my Wi-Fi, which actually isn't doing anything right now because I'm actually connected to my network through Ethernet. This is where you see all the different network activities. One of them is the VM I was running, I believe. So at the moment, I know Ethernet, this one, is the one I'm on. So I'm going to go ahead and click on it. In doing so, we'll start capturing packets on this specific network. And these are not filtered at all. So you can see a lot of different packets are coming in. So before I start the actual demo, let's just sort of go over about what the different columns are for the packet capture. So of course you have the number of the packet, you have the time which you captured it, the source as destination, it's like the one Jeffrey mentioned, is like you have the source and destination for the IP, and then the different protocols, and then some various information and the length of the packet. Okay, so then moving on, for this demo specifically, what I'll be doing is on the left-hand side, this is an HTTP website that is provided by Unitics. I think that is how you pronounce it. But essentially, this is a sort of dummy testing website they have created so other people can learn from it. And through this example, what I'll be doing is I'll be browsing this website. And on the right-hand side, what should happen is you'll be able to see the different HTTP packet appear in our capture. And this can go to show like why connecting your computer to a public network that you don't necessarily know who is also connected can be potentially insecure. Some of your information, and like how when you're browsing in, logging in to some website, your information may be leaked over the network. So the first thing I'm going to do is I'm just going to refresh the site, saying that I have arrived here. And then I just sort of browse around at the various different things. So of course, you can like look at the paintings. You can browse different artists in here. Of course, this is all of a dummy version, so nothing here is actually being leaked. Okay, but the important part is, let's say today this isn't a dummy website, and this is just a standard HTTP website that I want to sign up on. You'll go here, and you will fill out the sign up form. So this is a username, password. I just type in a random password. And then credit card number, some random totally invalid number that is way too long to be true, and then so here you have see that I have filled out the username form, and the moment we click sign up, it will essentially send a request to the server. In this case, it will be a post request to create this new user. And then the server responded, and then it gives me all of my data back. So in that event, supposedly all of my network activity of me clicking around on this website will be captured by Wireshark on the right-hand side. So the problem right now is, since I've been capturing for quite a while, there is a lot of packets streaming in. Oh wait, what's going on? Why are the HTTP not showing up? Oh, I might be on the wrong network. No, am I? Oh no, I'm on the wrong network. This is so sad. There we go. So let me fill out the sign up form one more time. And then some gibberish number. Okay. So let's go ahead and sign up. I'm not going to save it. So we have the verification sent back. And let's say if I don't apply the filter right now, there's a lot of packets that has been captured since I started. And what we want to do, the first thing is, since this website is essentially an HTTP website, we want to specify the HTTP packets. So to do that, what you want to do is on the very top bar, there's a display filter bar that you can use. And in this case, since we're looking for HTTP, we'll type this in. And then this will give you the various different HTTP website that has occurred since we started capturing. I'm actually going to stop the capture right now. And you can see here we have some GET request and here's the POST request that I used to create the sign up. So let's go ahead and analyze this. So to do that, let's just go ahead and right click on it. And immediately you can see that the password I have inserted is showing up in this really nice form item format by Wireshark. So this is assignment information. You have Henry, the test 1, 2, 3, 4, the really long credit card number that I created. So this goes to show that HTTP, how did you get to that Windows again? Yeah, so you if you find the specific packet that you want, what you do is you can just right click on it, or sorry, not right click, but left click. It's sort of like how you open any app. This will bring up this specific window. If you just left click once, you can also see it down here. And down below, you can see the actual bytes of the data and also the mapping to the specific text on the side. Does that answer your question? Okay, so let's take a little bit more time to look at what else is in here. Of course, you have a GET request, and over here you can see it's fetching the image, the logo image. So you can actually see the URI for this. If we open it up, here's the logo for the website. To view all packets through and not just. Yes, Wireshark does allow you to see, because you're connected to a network, and Wireshark actually captures all the different packets on that network. Okay, so this goes to show that a lot of the information that you're doing on an HTTP site is very insecure. Somebody on the same network can easily get the information. Okay. Yeah, I will make sure to read the questions out loud. Sorry. And then, of course, Google Chrome actually shows that it's not secure. So now what I'm going to do is I'm going to move on to an HTTPS site, which is a secured version of the HTTP. And you'll be able to see why most of the website now has transitioned to that specific protocol over HTTP by itself. So let's go to our favorite website, coolmathgame.com, and allow me to restart a new packet capture. And let me log out of here. Okay, so again, the packet capture is going live, and I want to go ahead and log in here. And of course, now that we have logged in, I can click around. I'm also not sure why my username is that, but it is what it is. But you can see the different games on here. And then now, if we do the same thing that we did for the HTTP website, first of all, you can notice this is different because of the secure lock on Chrome. You can also double click on it to see the HTTPS header. So if we go to HTTP, you will realize there is actually no packet under the HTTP protocol. And instead, what happens in HTTPS is before you send information over the network, the sender, how did he restart the packet capture? Okay, so real quick, to restart the packet capture, first of all, you can stop a packet capture by pressing this red icon on the top. And yeah, this is sort of like the stop recording. And then also immediately next to it is this shark fin symbol that says start capturing packet. Okay, I think that answers your question. So let me move on. So instead, what HTTPS does is before they send information over the network, it makes sure to use a key to encrypt the information, and then it will send it over the network. And on the receiver side, they will have something similar to that's used to decrypt the information. Therefore, not everyone on the network will be able to see the information. And HTTPS pass through this extra layer, or they go through this extra protocol called a TLS layer. If we do a quick Google search, you will know that TLS stands for Transport Layer Security. Yeah, so that's the difference between HTTP and HTTPS. That will be at the end. That's like basically the end of this demo, showing you the difference and also how to analyze HTTP packets. Yes, the S in HTTPS stands for secure. Yeah. Does anyone have any questions regarding the specific demo at the moment? Oh, and just to throw in more information, Wireshark itself is not able to recognize the HTTP, but if you do have the key for the HTTPS on either side, like either the sender or the receiver, and you insert it into Wireshark, Wireshark will actually be able to determine these TLS as actual application data, like how we saw it in HTTP, because right now you can see that a lot of these information are encrypted. What makes HTTPS more secure? So yeah, it's encrypted before you send it over the network. So generally there's like something called a ca.pem file, if I remember correctly, or I think it may name something differently, but there's a certificate on the sender side. And it will encrypt the information before you send it over the network. Okay, how do you get this when you send, if it's something you send and receive? I'm a little bit confused about that. So how do you get the key? Okay. Yeah, I'll let Peter and Will answer that question in the chat. But the question was generally, how do you get the key? And the key is like generated beforehand between the user and the server. And they will exchange like a public key. Okay, so I'm gonna go ahead and move on to the second demo. And the second demo can be found, oh God, Zoom, why? Let me close these tabs. So this is the slide for demo 1, analyzing the packet. So over here, we are going to be going over a packet capture made by, that can be, like the entire tutorial can be found on Medium on this link in case you sort of fall behind, but I'll be going over this and also showing the different tools to analyze a specific packet. And the general gist for this packet capture is somebody has connected to your remote server and they're creating a new user, so they'll be able to have access to it later on. So first thing, let me close this and re-download. Yeah, so you can use the link in the slide to download the packet capture. And need to move this, rogue user 3. And since this is okay, I'm gonna leave the chat to the other officers while I continue this demo. So since this is a pre-captured packet that what you can do is you can automatically just open it like you do for any other file. And since it's a PCAP or a PCAP-NG file, Wireshark will automatically detect that the file format and open it. So in this case, you don't have to select the specific network that you're connecting to that you want to analyze. So I'm going to make this full screen so everyone can see this a little better. And as you see, once again, we have a lot of packets, or actually not a whole lot, but it will still be a little cumbersome to go through and look at all of the different packet and then opening them up one by one. So generally we want to apply some sort of filter to help us better format the information. So underneath statistics, there's you can view something called a protocol hierarchy. And if we open it up, you can see that for this specific packet capture, there's the Ethernet, which is in this case will be the physical layer, or no, it'll be, and yeah, physical layer. Then you'll go into the network, and then you have the UDP, and you have the TCP protocol, which are two different kinds. And if we expand here, you will be able to see that within the TCP protocol, there are some packets with data. And this is the one, these are the packets that we generally want to focus on. So then what we can do now is we can actually select the data format, right click it, and apply it as a filter. So if we do so, this will leave us all of the different TCP packets with data inside them. So looking at this screen without clicking on anything, you can immediately see the stream index. There's 0 and 1, meaning there are two different streams of TCP data. So to analyze these packets, of course, you can click them, open them one by one. You'll be able to see the text by itself, but generally you want to sort of combine these packets together and wait, so we click beneath the TCP tab. So the thing about the data or like the protocol hierarchy is if you want to find, the data doesn't necessarily always apply inside, it's not always found inside the TCP packet. In some cases, it will be under HTTP. In some cases, it might be under a different protocol. So in that case, yeah, you can also just type data in the filter bar. Okay, you got it? Okay, so I'm going to continue. So here you have the stream index. So if you want to view them one by one, you can like click them. You'll be able to see the different bytes. It will translate to some text if it's available to you. Or if you want to sort of like look at them in the chain, you can follow them. And in this case, since we had TCP packets, it will be a TCP stream, and it will put everything together for you. In this case, you see, hello, packet analysis is fun. Let's see what else we can do. But this doesn't seem like the packet that we want. We wanted to see a rogue user inserting into our server and create a new user. So this doesn't seem to be the correct stream index. So instead, we're going to go and open stream index 1. And then doing the same thing, we want to follow the TCP stream. And in this case, you'll be able to see the conversation between the remote shell and also the rogue user. So inside the red, you see the different command that the user is typing in. In this case, it's like, who am I? They say you're the root. And then also here's some other command like this, all the different directories that you can access. So if you scroll down a little bit more, you'll eventually find that at some instance, this user created Marcel as the new username, and then he typed in his password. And then afterward, he did the cat etc's shadow to show that he has been successfully added to the database, as you can see under here. So these commands are just Linux commands to create a user, and they can actually be different things. Yeah, like he can do whatever he wants, but it will be shown in here. Yeah, so that's the end of the second demo. Does anyone have a question about it? I thought that was encrypted. So in this case, we weren't using SSH. So if it is SSH, like For example, if I'm connecting to the UCLA remote server, okay, sorry, let me repeat the question first. So Alex asked, wouldn't the user be SSHing into the remote server? So they can, but in this case, he isn't. He's using TCP to access it. So this is why we're able to see the different information. And how do I get the final window open? That is done by following the TCP stream. I can demonstrate that one more time. You simply right-click on any of the packet in the stream. And then one of the option is follow the TCP stream. And this will show you how do you know to go to TCP stream equation 1. Okay, so how I got to TCP equation 1 is, and I was able to see the different stream index. So there's only 2 stream here. And since when we follow TCP and stream index 0, it gave me this, and this isn't the information we're looking for. My conclusion is, let's just go and check out the next stream. And then in this case, it will be stream index 1. So I just changed the 0 to a 1. Of course, you can go back to the data and then start from the 1 and follow it from here as well. Stream index, I believe you have to set that actually. So that'll be set under preferences. Inside the column, stream index, it'll be a custom type, and then for the field, just type in tcps.stream. Yeah, that's how you get that to show. But I don't actually think being able to see the stream index is a huge important part. You can always just type tcp stream.equation 1 or 0, or like just filter, like sort it by that. Yeah, you can also use a column for specific form fields. All right, does anyone have other questions regarding this demo? No question mark? Okay, if that's the case, for the conclusion, this is like other tools that we believe will be useful for the challenge for today. In some challenges, you do want to be able to convert the bytes to ASCII. Scapy, on the other hand, is a little heavy-handed, actually. You don't have to use it. Actually, it would probably take a little bit too much time, but that's a tool that a lot of that can be used to manipulate and also send requests over Wireshark. You can use it to like fake packets, but it's not necessarily for tonight's workshop. The similar case was T-Shark. It's not necessarily, but if you want to use it, you might find it helpful on some of the challenges. All right, so that should be the end of the presentation part of the workshop. Any last minute questions before you guys break out? And
cool. So this is a simple catch. Let's see. So I guess a bunch of packets here. We have UDP, TCP, HTTP, MDNS. So I feel like if this is a really low value problem. So usually in the CTFs, like the first thing I like to do is literally just use this magnifying glass, which is fine, and I'll look for a string within the packet bytes. And so, and then usually there's like a format to it. So I'm gonna look at the format flag, and what do I get? Oh wow, value. Always trust the log. So I think this is our flag. So that's one way to do is just actually just look at the value flag. Another thing you can do is filter out the HTTP requests. See, there's only 2 right here. If I inspect this packet here, you see it's a post request into a login with the query mode being login. Oh, question in the chat. Okay, sorry, I was going a little bit too fast. So yeah, I'll repeat what I was saying. So basically how I got to the flag is to use the magnifying glass and then type in the string flag Make sure you have it set to packet bytes. So actually look at the info and the bytes that are stored inside the packet. And then use the string value and then press enter and it'll search the list of packets until it has found a match. As you can see here, the value of the flag is here. And then I can actually inspect the packet and see that this is part of a form that was probably sent from a login page with the key and corresponding values. So this is probably the username. And here we have the password item, which is flag always trust the log. Okay, yeah, so the magnifying glass is this button right here. It's find on Wireshark. Hopefully that answers your question. Right. Yep, cool, no worries. Okay, so that's this question, warm up. Let's do Cookie Monster. All right, so Cookie Monster, kind of the same idea. Let's start from all the packets right here. We have all the packets. Let me just minimize this. Actually, bottom. All the packets probably want to do the same thing. As we click the magnifying glass and look flag. Always go with the simplest solution first and try that. And then if it's not successful, then you kind of iteratively try more complex solutions. So I can look at the word string. I do get a response. I get flag under cookie pair under this packet. Okay, so I think this is on an HTTP request. So I can filter out that by HTTP. And then check this out. Okay. Okay, so what do we have here? Let's look at the packet. So this is the IP header right here. This is the TCP header, source port, destination port, and then this is the HTTP header. So just like the slides, the 4 layers, right, of the OSI model and the TCP IP protocol suite, they're all appended each other into this packet to make a frame. And so I think what we're really concerned about is just the application layer, and we can see the key and value. I'm just going to inspect here. Let's see, user agent set cookie right here, cookie pair, and where was flag? Flag is right here. So cookie pair is the key, and then the value is flag. And so this is our flag, right? But there's some sort of encoding on it. There's a double equal sign. So usually when you see the double equal sign, the first thing I think of is, let's see, copy. Let me just copy the bytes here. The first thing I think of is base 64, which is a type of encoding. And so we can just go online and we could go base 64 decode and type. Oops, that just actually copied the entire thing. Let me just try to copy the value right here, flag, and then we can just take this out here. And so we can decode this, and then bang, we have the flag. I am but a small island. All right, so yeah, those are the solutions for a simple catch and Cookie Monster. Let me know if you have any questions.